Okay, so we're going to start talking about some new vocabulary words. Some of these we've heard before, actually. So perpendicular bisector. So bisector is something that cuts something else in half. So we've had angle bisectors, and an angle bisector is a line segment or a line that will cut an angle in half. So here we have two equal halves there for that angle. And if I do a line segment, or segment bisector, there we go. That segment is now cut into two equal halves. So a perpendicular bisector, all that is that it bisects a side. So here, this is now cut into two equal halves. That's a bisector. And it's also perpendicular to that segment. Not all segment bisectors are perpendicular bisectors. For example, here, this segment bisector bisects this side, it's two equal halves. However, this is not a right angle. So this is our perpendicular bisector. In a triangle, we could have three perpendicular bisectors because these are going to be three segments, so three perpendicular bisectors. Something like here. So here you can see that this blue is perpendicular to that side, this green is perpendicular to that side, and this red is perpendicular to that side. Notice it's perpendicular here, and it bisects this side. It does not bisect the other side, and that's important. So this red line is probably the most obvious, or even the blue. It bisects the side that it's perpendicular to, but the opposite side is not bisected, and it's not perpendicular to that side. These three perpendicular bisectors will intersect inside of the circle, and we call that the circumcenter. So this circumcenter is the intersection of those perpendicular bisectors. So here's just some theorems. This is taken right from the textbook. Just saying any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. It's wordy, but this picture is actually nice. So here is a perpendicular bisector. And so notice here at point A, that is going to be equidistant, so it's the same distance away from point C as it is to point D. So these are the endpoints. Same down here with B. So we know we have this line segment CD. It's finite. If I have this perpendicular bisector, if I choose any point on that perpendicular bisector, let's say B, B is going to be the same distance away from C as it is the same distance away from D. That's what this theorem says. Now, 5.2 here says that any point equidistant from the endpoints of a segment lies on the perpendicular bisector. So this is pretty much what we just looked at, just going in a different direction, if you will. So here we can see that if we have perpendicular bisector, a point on that perpendicular bisector is going to be equidistant from the endpoints. Simple enough. Now if we say, hey, I have some point floating around in space and it's equidistant from the endpoints, that lies on some perpendicular bisector. So if I actually draw, there's a segment, and I'll make a perpendicular bisector, close enough, and actually, no, I don't want to do that, right? What I want to do is just have some point floating in space. So here's point A, here's point B, and if I just choose some point, I don't know, point C, and I say, hey, that's equidistant away from A to B, it's the same distance. If I draw a line that's perpendicular to the line segment, I don't have to do any calculations. I know that's going to cut this in half. So if you think about some applications here, we can actually do a lot involving congruent triangles and isosceles triangles with this. So this is actually a very helpful concept. All right, next piece of information is an angle bisector. We should know what an angle bisector is. An angle bisector is a line or a line segment, or in this case a ray, that cuts an angle into two equal halves. Inside of a triangle, there are three angles. So if we intersect the three angle bisectors, they will intersect at the incenter. So the incenter is the intersection of the three angle bisectors inside of a triangle. A couple theorems to go along with this. So any point on the angle bisector is equidistant from the side. So if I have this angle bisector here, and I have some point here, I calculate my distance going perpendicular to the sides, so as best I can draw. So just like that. So EF, and I don't know, call that G. So any point along this angle bisector is going to be the same distance to either side. Now any point equidistant from the sides is going to be on the angle bisector. So again, just like before, we have just a different way of looking at it. So if I have some point floating around, I know it's the same distance away from two sides of a triangle, then I know that's going to be on the angle bisector. Next we have the median. So the median is just like an angle bisector, except it goes through the opposite side in half and cuts the other side in half. So here the median is actually like a segment bisector, but this is not a right angle. Notice these are not perpendicular. And that's what a median is. When we have the medians intersect, so there are three medians, that's called the centroid. So kind of just going back here. So if I connect this to the opposite vertex, that is the median. So notice, especially this blue line is probably the most obvious. The angle is not bisected, and the segment is not perpendicular. So it's not a perpendicular bisector, but it is absolutely a bisector. And this is not an angle bisector, but it does intersect with, it does go through it. Next up is an altitude. So an altitude is just like a median in that it connects a side to the opposite vertex. However, it doesn't cut the side in half, but it is perpendicular. And so we have three altitudes inside of a triangle, and we call that the orthocenter. So three altitudes linked up, intersecting to make the orthocenter. And so here are just some key theorems here. So the circumcenter theorem says that the circumcenter of a triangle is equidistant from the vertices. Now we have to think back to what a whoops, don't know what I hit there. Okay, we have to think back to what a circumcenter is. So let's look back at the picture. There we go. And here we have these perpendicular bisectors, right? So if we have the three intersecting points of perpendicular bisectors, that is a circumcenter. And so the circumcenter is going to be equidistant to all the sides. So here you can kind of see this jumbled up picture, but there's one perpendicular bisector. And you can see that is going to be equidistant to all the vertices. So if I kind of go over this with my marker, computer's being slow. Well, you get the idea. Here's my perpendicular bisector. And we can see that this point is equidistant to B, to A, and to C. Can't draw a straight line, but that's what the circumcenter theorem says. The in-center theorem is equidistant from each side. So while the circumcenter is equidistant to each angle, the in-center is equidistant to each side. Now the centroid theorem is cool because the centroid theorem says that the centroid is located 2/3 of the distance from a vertex to the midpoint of the opposite side. So don't forget that a centroid here is the intersection of 3 different medians. So if we have this intersection point of the 3 medians, each median is going to be cut into a ratio of 1 to 2, so 1/3 and 2/3. So here we have all these different segments. It may look like we can't solve this, but we actually can by writing equations. So if I look and I say, let's look at SF. So SF is a median, because I know that this point here is, okay, well, S, T, and U are the midpoints. So if we look and we see that these are lines going from a midpoint to the opposite vertex, we know it's going to be a median, and the median for all 3, the intersection of all 3 medians is the centroid. So this point right here is a centroid. So we know that 2/3 of SF is going to be the larger segment here, and that's 4.6. Well, SF is 4Z plus 4.6. So 2/3 of 4Z plus 4.6 is equal to 4.6. We can get rid of this fraction by multiplying both sides by 3/2. And so that leaves us with 4Z plus 4.6. Here, if I divide this by 2, I'm going to get 2.3. And if I do 2.3 times 3, I'm going to get 6.9. So 6.9. And then I can subtract the 4.6. So I get 4Z is equal to 2.3. And then I can divide both sides by 4. So 2.3 divided by 4 is going to be 0.575. That's how we get that. And well, really, if these are 1/3 and 2/3, another way to think about it too is that 2 times AT would be equal to dA, right? Because if this is 1/3 and that's 2/3, double this is this side. So 2 times of 2x minus 5 is equal to 6. So 2x minus 5 is equal to 3. So 2x is equal to 8. So x is equal to 4. If we check that for this one, this is 8 minus 5, which is 3. This is 3, and this is 6, so this is double that. The whole distance is 9. 2/3 of 9 is 6, and 1/3 of 9 is 3, so that all works out very nicely. And then down here, I mean, really just the same approach, right? So 2 times UA is going to be equal to AE. So 2 times 2.9 is equal to y, so we get 5.8 is equal to y, and that does it for us. So this is a very, very important theorem. So make sure you can think logically. Don't worry about just knowing how to repeat the problems that I do. Understand how I actually go about doing these problems. That's the more important part. And so here we have some other application type problems that we can look at. So BD is a median. So that means that 6x plus 3 is equal to 7x minus 1. So if I solve this, I actually get that x is equal to 4. For number 2, D, E, and F, so D, E, and F are all midpoints. So these are all medians. AB is equal to CB. So that makes this an isosceles triangle. What do we want to do? We want to find x and y. Not that big of a deal. So if that's 10x, this is 10x. And this is 9x plus 6. So we know that 2 times 10x is equal to 2 times 9x plus 6. That 2 times is a little bit unnecessary there, because we're just going to divide it out, and we get that 10x is equal to 9x plus 6, which means that x is equal to 6. And we also know that 3y is equal to 15. 3y is equal to 15, so that means that y is equal to 5. Down here, EH is equal to FH is equal to HG. Okay, so if EH is here, that equals FH. We just set those two equal to each other, so 9x minus 2 is equal to 7x plus 4. So 2x is equal to 6. So x is equal to 3. Well, if x is equal to 3, this side right here is 21 plus 4. So that's 25 is equal to 5y. So y is equal to 5. Whole bunch of drawings on this one, but notice these are all medians. And so that means that this is the intersection of medians, which is a centroid. And so a centroid, we have that special theorem. So here we know for x, we know that 2 times 12 is equal to 2x. So x is equal to 12. We know that 2 times 10 is equal to 3y plus 5. So that's 20, so 15 is equal to 3y, so y is equal to 5. And we also know that 2 times 6z is equal to 24, so z is equal to 2. So there are our answers. See how it would be impossible to get this problem if you didn't know what a median was, if you didn't know what the centroid theorem was. And then finally here, so our second to last, penultimately, D is a centroid of ABC. Yet again, same centroid theorem type problem. So if we look, 2 times 6x is equal to 24. So that's 12. So x is equal to 2. For the y's, 8y is equal to 32. Oops, so 2 times 8y is equal to 32. So that means that y is equal to, whoops, getting ahead of myself. Y is equal to 2. And then finally we have that 2 times 6z is equal to 9z plus 6. So this is 12z is equal to 9z plus 6. So 3z is equal to 6. So z is equal to 2. And then over here we have V is a centroid of triangle RST. So TP is 18. So X is a smaller segment, so that's 1/3 of TP, which is 18. So X is equal to 6. MS is, so Y is yet again the smaller segment, so that's 1/3 of MS, which is 15. So Y is equal to 5. And then Rn is equal to 24. So that means that, whoops, not Rn. Rn is 24. So Z is yet again the smaller segment, so that's 1/3 of 24. So Z is equal to 8. And there we go there. So those are those problems in application. So they can get really tricky, but look at the math. The math is not the challenging part. The challenging part is knowing the concept. How do I know how to set this up? That's just the centroid theorem. So make sure you know the vocabulary. Make sure you know what a centroid is, what an orthocenter is, and all these different vocabulary words. If you know that, then doing the problems becomes that much easier.